Hey everybody, this is a video for my MCI45S Intro Calc course. This is the lesson for finding the slope of a tangent to a curve, and I just found this cute little picture that reminded me that if you're having a hard time kind of visualizing what a tangent is, imagine that the tangent is the skis of a skier on a very hilly slope. So notice that the skis just barely touch the curved slope at one point, and that's what a tangent is. And we've been talking about tangents quite a bit already. Okay, let me go to display capture here. And now we can go to our notes. Oh, there we go. Feel free to pause if I'm going a little too fast and copy this down, or paraphrase it any way you'd like. So this is lesson 1.4, the equation of a tangent line. We have previously seen that we can find the slope of a tangent line by approximating it using a sequence of secant lines with a decreasing distance between its intersection points. Let me again remind you what that looks like. So going to Desmos here, there we go. There is a curve, a very nice curve of some point, and I've got myself 2 points. I'll call them P and Q. Q is a definite point. I've decided that Q is going to be 2 and then something. And I am just going to close the gap of this secant. I'm going to get, if I want to know the tangent line at Q, what I have to do is I have to bring this point P closer and closer and closer. It kind of looks like it's going to be a horizontal line, this tangent line, doesn't it? Maybe it is. I don't know. We'll have to do the math on that and see. But you get the idea, right? The closer I make the distance between A and 2, then the more this secant approaches being a tangent line. And that's a very important idea. And we are going to, as we say in the notes here, we're going to formalize this idea using algebraic symbols and limit notation. So I'm going to basically draw the same graph I was just using. In fact, here, if I kind of zoom out to the home position, as you can see, oh, it's a lovely curve. So I'm going to try to sketch something like that. Let's see if I can sketch this fairly accurately. You don't even want to know the equations I had to come up with to make this curve kind of happen the way I wanted it to look. So something like that. Oh, lovely. And I'm looking for, there we go. Beautiful. So give me a sketch something like that. By all means, feel free to pause the video if you want to make it all pretty. And we are looking for, and again, I'm going to call this Q. And I actually had a specific Q because I had to plot a specific point on Desmos. But let's say I don't really have a specific value for the x coordinate at Q. I'm just going to call its x coordinate x then. And I'm going to call its y coordinate f of x, right? The value that I'd get when I run this x number through whatever formula makes that curve. And I'm going to call this point here that I was dragging closer to it, I'm going to call that point P. And it's got coordinates, again, I'm going to call it a and f of a. Two numbers that, again, a I could just plug into whatever formula makes that, and it actually is a cubic curve if you really want to know. I guess I could put arrows on it. And a secant line, of course, is the line that joins those 2 points like so. And my goal is to continually shrink the distance from P to Q until, and this is, of course, here, this is my secant. And I want to shrink those until I eventually get a line that gets touched exactly once. And I'm looking for a different color. Hello, where is my red pen? There we go. So something like that. That's my ski touching the slope. And that is, of course, my tangent line. And if I shrink the distance between these 2 points, I get the tangent line. Now remember that the slope between these 2 points is, of course, well, here's the slope formula. M is equal to y2 minus y1. That's the coordinates over x2 minus x1. You've been doing that formula since either grade 9 or 10. And we actually know that for the slope from P to Q, it would actually be, well, f of x minus f of a all over x minus a. So that would be the formula that I'm looking for. And again, take a quick look at that the graph, as I shrink this distance, notice what happens. The slope of the secant line is changing, right? It is definitely getting closer and closer to, I think, might be about 0. But I want to know what happens as the distance from A to that point Q, distance from P to Q, gets infinitely close. Right? It obviously can't be one on top of the other. It can't be the same point, because look back at the formula. If it was the same point, if x and a were the same place, well, what happens when you minus a number from itself? You divide by 0. And as we all know, dividing by 0 is very, very bad. Math won't let you do it. So, back to some exposition here. So the slope of the secant line, oh, I'm knocking pages around, sorry. So the slope of the secant line is the slope from P to Q, which is that. So I kind of already drew that in the diagram. Jot that down again, and then think about it this way. Think that as points P and Q get closer together, you approach a tangent line. So as, remember this symbol means, as x approaches A, you would say that the slope of the tangent at point Q is the limit as x approaches A of f of x minus f of A over x minus A. This is the important part of this part of the lesson. Put it in a little happy cloud or highlight it or whatever you do when you get a new formula. Yes, I'll give you the formula. You don't have to memorize it. But at the end of the day, it's not really a new formula. It's just slope, y2, y1, x2, x1. But what's important is that I've got this new part on it, this limit part. If you did all your homework for 1.2 and 1.3, you'll understand what a limit is, and you'll be able to calculate it. And we actually call this Formula 1, just like race cars. This is the formula that we're going to call Formula 1. So in your homework, when you see use Formula 1, they mean use that guy. Well, the existence of calling this Formula 1, of course, kind of pretty much guarantees we're going to have a Formula 2. There's going to be a sequel. And here's how that's going to look. I'm going to redraw my diagram. In fact, oh, you know what I'm going to do? I'm going to like trace it. So if you're continuing with your notes here, make another XY grid. Now, let's see if I can get the exact same thing here happening. Let's see, where's the grid line? The grid line's about there. Beautiful. So I want that same curve back. Curve. Now at the end of the day, I don't really care what this curve is. I just kind of like the idea that it's pretty... Oh, I'm off of it. But you get the idea. There's the curve. I just like the idea that it looks the same as the last one. So there's my curve. And let's see. This time we're actually going to think about slope again in a different way. Again, I'm going to have points P and Q. This time I think I might put P a little further down. So P's going to be down here. And again, the P is going to have coordinates A and F of A. And Q, this time, I'm again going to call it points X and F of X. But this time, and you know, now that I think about it, I've kind of put that in the way of what I want to do. That was not very smart on my part. I'm sorry. I hope you're working in pencil. Let's put the coordinates over here. A, F of A. You'll see why in a sec. Because I also, again, want to think about the slope of this line, or this line segment, this pretend line that we call the secant between here and here. And you know, there's another way to think about slope that we actually haven't really talked about yet this year. Remember that we can think about slope as this distance divided by this distance. Do you remember what you called that back in grade 9 or 10? You called it the rise divided by the run. So let's remember that the slope from P to Q could also be considered the change in y over the change in x, which is also, of course, known as the rise over the run. So I kind of need some sort of, what's the word I'm looking for? I need some sort of way to quantify the rise and the run. So what I'll do is I'll just quantify the run. I'm going to call this run a distance that we'll call h, right? So distance horizontally. from P to Q. Just the horizontal distance from P to Q across. So that means I can kind of rewrite what point Q is. Point Q, I could call it x1 and f of x, but I've got a better name for it now. Now, this is the a coordinate plus the h coordinate. So this is a plus h. And then, of course, didn't give myself enough room here. That means that I run that through the formula. This will be f of a plus h. See if you can get your head around that. Let's look at it on Desmos, where we can move things around. That guy. So here we go again. This is point P, which has coordinates a and f of a, whatever they are. And this is point Q, which is this a plus this h distance. And notice, I want to get these 2 points closer and closer together. Look what happens. Rise over run isn't becoming 0, but it is shrinking in the sense that now, remember that shrinking numbers for those distances doesn't necessarily mean a shrinking answer. Just on scrap paper here, just to illustrate that point, keep in mind that, you know, if I have the number 1 over 2, that's the exact same number as 1,000 over 2,000, or 0.001 over 0.002. Really, how big and small these numbers are don't really affect what the slope is. What affects the slope is, of course, the rise over the run as a ratio. So if you look at this thing and you think, okay, well, these 2 points are going to get closer and closer together, until what? Until h starts getting closer and closer to not existing at all. And I'm actually kind of feeling like I should make my little labels go away. Let's see if I can make the labels go away. You might not want to look at these equations any here. Here, go away label, go away label. There. Actually, well, let's make the other labels go away too. What else have I labeled? I labeled the point, I labeled that point. There, get all the labels out of the way. And now just watch h. As h gets smaller, I mean, the rise gets smaller as the run gets smaller, but they get smaller at the same proportion. So in other words, I don't change proportionally my slope as I get closer and closer. And what I'm really shrinking here is I'm shrinking h. So I would like to explore what happens as h approaches 0. That's the important part here. So, first of all, how do I describe this slope? Well, I'm still going to use basically the slope formula. But my slope formula is going to look like this now. So my slope formula is now going to look like this. Here, let me just pull that over. There we go. This is formula 2. Notice that the slope of my tangent, which would happen when h gets closer and closer to 0, is that. Now, where did that come from? Maybe I've skipped a step here. Let me put it back. This comes from the formula again. Slope is y2 minus y1 over x2 minus x1. Only this time y2 is, oops, wrong page. y2 is right here, right? That's y2, and I missed a bracket, I just realized. This is x2, this is y2, this is x1, this is y1. So plug those things into the slope formula, and you get f of a plus h, that's y2, minus f of a, all over, so that's y2 minus y1. This is x2 minus x1. And of course, this will be the slope of the tangent as h approaches 0. So the slope of the tangent is this as h approaches 0. Do you see how this simplifies? I can't simplify f of a plus h or f of a, so they're going to stay the same. But I can simplify the denominator. a plus h minus a, that bracket doesn't really mean anything, is just h, and that is formula 2. So formula 2 tells us that we can use, remember this kind of algebra from the last assignment? We can use situations where we plug in something to the function and then try to figure out a way to make that h go away so that when I plug in 0, I don't end up dividing by 0. So I think it's time to do examples of both formulas. Let's do an example for, first of all, using formula 1. So let's start by just kind of thinking about the question. Find the slope of the tangent to the curve f of x equals x squared plus 2x minus 1 at the point 2, 7. Okay, what kind of a curve is x squared plus 2x minus 1? Should be fairly familiar to you. You did enough of these in grade 11 to gag a goat. It's a quadratic function, so yep, it's a parabola. And we're going to use formula 1, which means we're going to take the limit as x approaches a of f of x minus f of a over x minus a. Now obviously I have to use this point, and this point tells me a and f of a, right? This is a, this is f of a, right? I put 2 into this formula and I get 7. Try it if you don't believe it. So I am going to do this algebraically, and I just froze my screen. Come back to me, screen. There we go. Holy cow, I don't know what happened there. So this is the limit. I'm going to just see if I can focus that a little better. Oh, that's prettier. Okay. The limit as x approaches 2 of, so f of x minus f of a. So see if you can kind of get your head around what that's going to look like, right? So that's going to be f of x. What is f of x here? Well, f of x is this function. So that's going to be x squared plus 2x minus 1 minus f of a. Okay, well, we just decided a is 2. So I want f of 2, right? So what does f of 2 look like? Well, f of 2 looks like this. A 2 goes in where the x is. A 2 goes in where this x is. And then minus 1. And remember, I'm minusing all of what f of a is. So use a bracket so that you remember that you're minusing all of that expression. Okay? That was a mistake a lot of you made on that first quiz when you had a question similar to this. You didn't make that a bracket, so you kind of ended up with the wrong number. And then down in the bottom, it's x minus a, which, well, I don't know x yet. I know I want to put in the number 2, but notice a is 2. So if I plugged in a 2 right now, I get that dreaded divide by 0, and I can't have that. So what I'm hoping is that when I simplify this stuff out at top, I can somehow get rid of x minus 2, or I can use one of the tools in my algebra toolbox to help me get rid of it. So that's my hope. Otherwise, maybe I can't find the limit for this if I can't find a proper algebraic tool to get rid of x minus 2 in the denominator. But I'm pretty confident we can do this. The limit as x approaches 2, some of you probably see it already. This is 4 plus 4 is 8. 8 minus 1 is 7. So this is x squared plus 2x minus 1 minus 7 all over x minus 2. I'm going to simplify that to the limit as x approaches 2 of x squared plus 2x minus 8 all over x minus 2. And what's the algebra method that's going to make my x minus 2 go away? You guessed it, it is going to be factoring, because that trinomial on top there factors very nicely. It is equal to the limit as x approaches 2 of x plus 4 x minus 2 all over x minus 2. I guess you probably could have figured out that there was going to be an x minus 2 involved. Now that these are terms, or sorry, these are factors and not terms, you can divide them to get an answer of 1, which means it's x plus 4 times 1, which is just the limit as x approaches 2 of x plus 4. No more denominator. Yay! So I can now plug in my 2 very happily. Remember, when you do that, the limit's gone. 2 plus 4 is 6. So I think the slope of that curve at that point is 6. And the question didn't ask it, but I'm going to actually add a little something to the question. I'm going to add the following. I'm going to add, find the equation of the tangent line at the point 27 to that curve. So I already know, I've already figured out that the slope is 6. And again, if you think back to the grade 11 review that we did of our algebra, one of our skills was, can we find an equation given a slope and a point? And yeah, we can. We can use the formula y minus y1 equals m times x minus x1, also known as the point slope form of an equation, of a linear equation. So I know this, that y1 here is 7, and I know that my slope is 6, and that's x minus 2. Now, it didn't say what form it wanted the answer in, so I'm very happy just leaving it in point slope form. But let's check that out and make sure that that this makes sense. You can check on Desmos if this works. If this works, when I graph this line, this curve, and I graph that line, it should look like a tangent, or else I've done something wrong. So let's have a look at that. I think I did it right here. There we go. There is the there's the parabola, and there's the 0.27, and here's that line that we just solved for, and as you can see, that just touches it exactly in one place. In fact, if I zoom in like forever, it looks right now like it's one line. I guess I have to really zoom in to see some separation at this scale. It looks like it's all one line, but it is not. Let's see. Zoom, 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 zoom. Oh, it looks like it's going to make a liar out of me. I've zoomed in so much that I guess the thickness of the line is kind of taking over. You can kind of see the colors change. I'm going to have to go a long way now to see some separation between the lines. If you ever do this to yourself and you get lost in space on your graph, you can always just hit home, and it goes back to where it should be. And I guess, yeah, you'd have to get around somewhere between 10 and 12 to see that there's definitely some space between those. And yes, that is a line that just touches that curve at one spot. Isn't that lovely? I hope I didn't make you all dizzy by scrolling around like that. Anyway, let's go back to our piece of paper, and let's do an example of the other formula now. So the other formula is formula 2, and there's the example we're going to do. Find the slope of the tangent to the line y equals x squared plus 5x minus 1 at x equals negative 3, and use formula 2. And if you're wondering what's with all the parabolas, well, we know that you guys coming out of grade 11 did a lot of parabolas, so we would hope this is fairly familiar to you. That's the idea. We want it to be familiar. Let me sharpen my pencil, and let's tackle this. So what are we going to do with this? Well, we're going to use formula 2. And formula 2 is this guy right here, right? M is equal to, the slope is the limit as h approaches 0 of f of a plus h minus f of a all over h. So how much is a here? Well, a is just this x value of negative 3. But I actually need to know f of a. So what's f of a? Or in this case, what's f of negative 3? So let's run negative 3 through there. So y is equal to negative 3 all squared plus 5 times negative 3 minus 1. And when I run that through, let's see, I think I'm going to get negative 7. Am I right about that? That's going to be 9 minus 15 minus 1. 9 minus 15 is negative 6 minus 1, yep, is negative 7. So this point here, negative 3, actually gets to be negative 7. There we go. So that, again, is a, and that is f of a. All right, I think I'm ready to plug this into my formula now. So I think I might do this on a new piece of paper. Let's see, what did I put under this? Oh yeah, I got a blank piece of paper. Okay, so I'm going to start this on a new piece of paper because this is going to take some room. This formula usually ends up being a little more complicated than the other one. So let's see. M is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. And I just figured out that a is negative 3 and f of a is negative 7. So here we go. And of course, f of x is, what was the formula again? X squared plus 5x minus 1. So that's all that I need to get this done. This is the limit as h approaches 0 of the function with a plus h in it. So a is negative 3, h I don't know yet. So basically it's going to be negative 3 plus h, which is probably easier to write as h minus 3, right? So a plus h is like saying negative 3 plus h, which is like saying h minus 3. So hopefully that doesn't confuse people. So I'm going to plug h minus 3 through this formula. That's what this is telling me to do. F of a plus h is telling me to put this through that formula. So that's going to be h minus 3 squared plus 5 times h minus 3 minus 1, and then minus f of a, and I already figured out f of a is negative 7. So minus negative 7. Watch out that you're minusing a negative there. That's an easy place to make a little mistake. All of that over h. All right, I'm going to have to use some algebra on that. Remember that the goal eventually, I can't plug 0 into h because then I divide by 0. So hopefully whatever happens on top here, I'm going to end up being able to cancel out that h. That's the goal. Otherwise, I can't find you an answer for the slope of this line. So that's going to be h squared minus 6h plus 9 plus 5h minus 15 minus 1 minus negative 7 is plus 6. And all of that is over h. Look at what's happening here. Check out those constants. Do you see what's happening? 9 minus 15 is negative 6. Negative 6 plus 6 is 0. Isn't that nice? Why am I so happy to see that the constants went away? Well, because now I can simplify the like terms of the h. And now I can actually do this as a divide. Now, careful. I'm going to actually make a mistake on purpose. People do this all the time. It drives me crazy. Absolutely nuts. They look at h squared minus h over h and they go, oh goody, I can cancel the h's. Oh, that was physically painful to do because it's just so wrong. Really? Really you think that's how math works? If you had 5 minus 2 over 2, think about that. That's 3 over 2. You think it's 5? Or 5 minus 1? It's neither of those things. You can't cancel like that. So make sure that you understand how to cancel properly. What I mean by that is you can only cancel factors. You can't cancel terms. So what I'm going to do is I'm actually going to take one more step here to make sure that I see properly how to do this. I'm going to factor an h out of the top. And now that's a factor. So h divided by h is 1. This is the limit as h approaches 0 of h minus 1. There. No more denominator to have a hassle with. Plug in my 0 where h is, and I get 0 minus 1 is negative 1. So I think that the slope of the tangent is negative 1. And just for fun again, what if I had to find an equation for that tangent line? So equation of tangent is, let's see, so what was the point that I used again? Oh yeah, it was x is negative 3 and y is negative 7. So the equation of the tangent would be y plus 7 equals negative 1 times x plus 3. Let's see if Desmos says that that line really is the tangent to this curve. Let's check that out. I'm very curious. Oh, there's my iTunes. Isn't that nice? Okay, so let's see. I think that's the last thing I put together. There it is. There's the curve. Let's put the point down that we want. We want the point negative 3 comma negative 7, which you can't see right now. There we go. Now we can see it. And I think that if I type in the line y plus 7 equals negative x plus 3, oh, look at that. It's a ski on the ski hill, just very upside down and some sort of gravity-defying ski hill of some sort, but you get the idea. That green line touches that curve at exactly 1 point, and it does so with a slope of negative 1. And that's the kind of math that you're doing. This is the kind of stuff Sir Isaac Newton invented so that he could solve problems in the sciences, specifically physics. He was a physics guy, that were stumping people. How do you find the rate of change on a curved line? And rate of change is slope. And how do you find the slope of a curved line? Well, we just showed you. We've given you 2 formulas. Now, for the homework, you're going to actually try some yourself. I'm going to make some videos of some more examples. I'm even going to bring in some examples from the sciences. and we'll post those in the next couple of days. Thanks for watching, everybody. Let's see, how long was that video? Oh, half an hour. Much shorter than the last one. Perfect. All right. Have a good one, everybody.